a simple quantum sketch with applications to graphite.
Hi, yeah, so thank you, Andrew. Yeah, so I want to tell you about a simple quantum sketching primitive and how you can use it to get provable quantum space advantage for a couple of natural streaming problems. And so I want to start by thinking about a very simple problem that you already know how to solve. And this problem is you have a set S living in some universe U, and you want a succinct sketch of S that solves the following two problems. So I want to be able to come along with another set P, also living in U, and estimate the size of the intersection between S and P to say error may be a constant times the size of S. And if these two sets have a decent amount of overlap, I also want to be able to sample a random element from within that overlap. Like I said, this is a very simple problem that we already know how to solve. All you have to do is take a constant number of samples from your set S and make that your sketch. So then, someone comes along with a set P, they want to estimate the intersection size, they just have to count how many of the samples land in their set P. And if they want to sample something from the intersection, they can just take one of your samples that lands in P at random. Okay, so we know how to solve this problem, but what if I make it a bit harder? Instead of having P be a set of singleton elements, I'm going to have P be a set of disjoint pairs from this universe U. And again, what I want to be able to do is estimate how much of the set S is covered by these pairs in P. And if it's a large enough fraction of S, I also would like to be able to return one of these pairs P at random. And so solving this with kind of a trivial sampling argument is going to be quite a bit harder because your probability that your random sample you took from S will include both elements of some pair in P is going to be a lot lower. And in particular, by the kind of standard birthday paradox kind of argument, the number of samples you'd need would be about the square root of the size of S. And you can actually show by a reduction to the Boolean hidden matching problem in one-way communication complexity that this is optimal up to a log factor. Any classical sketch that solved this problem would need a square root of S many bits. But if you've seen the Boolean hidden matching problem before, one thing that you'll know about it is that this problem actually exists to prove exponential separations between quantum and classical communication complexity. And so what I'm going to tell you about now is a sketch inspired by this quantum protocol for Boolean hidden matching that can solve these problems using only logarithmically many qubits. And so this sketch is going to let you do this cardinality estimation problem, count the number of pairs in P that are contained in S, and it's going to let you do the sampling problem. If enough pairs in P are contained in S, you'll be able to sample one of them. With the caveat if one of these pairs in P has only a size 1 intersection with S, there will still be some chance of returning it, but when you do so, you'll have a 50% chance of getting a -1 label. So imagine if you're doing anything in expectation with these samples, then you can still make sure it's correct. Okay, so how can we construct a sketch with these properties? I guess I should stop and say it's clear what we're doing, what the sketch can do. Okay. So to construct it, we're going to need a couple of quantum primitives. These are going to be the concept of a superposition. And so the way that you should think about this is that if you have some like classical universe U, a superposition will be a length 1 vector in the vector space, the complex vector space, where each basis element is one of the elements of U. And we'll use this kind of this ket notation to denote these individual basis elements. And in the same way that you can represent a single element of U classically with log size of the universe classical bits, you can represent an arbitrary superposition over U with log size of the universe qubits. Now, if we could take one of these superpositions and like extract every single coordinate of it, every single amplitude we call it in this context, then we'd be able to break all kinds of information theoretic lower bounds. But instead, we're restricted to accessing these superpositions via measurements. And there's a lot of ways of formalizing measurement. But the one that I'm going to use here is this idea of a projective measurement. So how this works is you construct a family of projectors on this vector space C to the U that sum to the identity. And to each of these projectors, you attach a label, which you can think of as a measurement outcome. And then when you do this measurement, your probability of getting a given measurement outcome is just the squared length of the vector after you project it down onto the corresponding projector. Because these projectors sum to the identity, it's going, these probabilities will sum to 1. If you could do these measurements repeatedly, you would also be able to extract all of the coordinates of the superposition and break everything. But instead, when you do this measurement is essentially destructive. Like when you measure a superposition, whatever your outcome is, your superposition vector gets projected down onto that outcome projector and then renormalized to be length 1. Okay, so with these two primitives, we're going to be able to build a sketch that satisfies the criteria that I mentioned earlier. And the sketch we do will actually be very simple. Our sketching state is just going to be a number of copies of the uniform superposition over the set S. Remember, the set S is the set that we wanted to sketch. And by that, I mean it's going to be the vector that's exclusively supported on the elements of S, and where the amplitude of each of these on each of these coordinates is going to be the same real number, which means that since it's supposed to be a length 1 superposition, it's going to be 1 over square root of the size of S each time. Then when we go to query this sketch, we're going to perform a measurement made out of projectors that we build from the pairs in our kind of query set P. And so these projectors for each xy, each of these pairs xy are going to be the projectors onto x plus y and onto x minus y. And because we required that P was a set of disjoint pairs, it's going to be possible to make these all sum to the identity because the corresponding projectors will be all orthogonal. So we'll just collect all of these projectors and then add one final projector that's just the identity minus everything that we've added. And so what are the outcomes of this going to be? Well, remember that the measurement rule is that our probability of seeing an outcome is the square of the length of the vector once you project it onto that projector. So in particular, for any pair, if xy is actually contained in S, then the overlap with the vector x plus y, or the projection onto x plus y, is going to be size 2 over S when you square it. And there'll be 0 overlap with x minus y. On the other hand, if exactly one element of the pair is in S, then you'll have an equal chance of getting either x plus y or x minus y. And if x and y, neither of them are in S, then there's no chance of returning either because there's 0 overlap with either of the corresponding vectors. And so this will let you solve both our cardinality estimation problem and our sampling problem. So for the cardinality, we can just use the fact that this rule means that the difference between your probability of seeing an x plus y and an x minus y is proportional to the number of pairs that are entirely contained in S, because you only get the two cases where they're not contained in S give 0 contribution to that expectation. And then for the sampling problem, we can actually just do this measurement and return, whatever we see, x plus y or x minus y, but with a sign of -1 if you see x minus y. And so that means that you obey the promise that we gave that, sometimes you're allowed to return a pair with size 1 overlap, but if you do so, it will come with a random sign. So that's how you can make the sketch. I guess I can stop and ask if there are any questions about that.
I have a question. This is probably, I just don't understand how super. Okay.
So you have this set, it's fixed, and then later I show up with these pures and I want to query basically how many of them are completely contained in the set. If I'm measuring, do I destroy my sketch so I can only do it? Oh, okay. So, okay.
So if you're wondering, how can you use this in the stream?
Or I guess what I was wondering was, if I have many, I guess I was imagining the scenario was I sketched this big set once and I have many different queries, but it's kind of like a one-time use thing.
Yeah, it is a one-time usage. Later, we'll see how you can do partial queries where you only query with one pair at a time and you only destroy the sketch a little bit. But yeah, it is a fully destructive operation.
Okay,
after
cool.
you do it, what will happen is your sketch will have been collapsed down to that pair that you output.
Okay.
I guess I would say that even in the classical case where you were doing sampling, it's still it's still a destructive operation if you care about your answers being correlated, right? Because
yeah, I guess that's right. Yeah. Although less destructive.
Yeah. Depending on your application, the classical one, you could use it repeatedly. And here it's one time only.
Okay, cool.
Are there any other questions?
Well,
There's a microphone coming your way.
I'm a bit curious about the idea behind this x plus y and x minus y measurement.
Mm-hmm.
Is it like an inclusion-exclusion thing? Say if I have more than a pair, if I have a set of size n, do I have to query 2 to the n times like that?
If you had, it's actually worse than that. If you had sets of larger than size, so if you had sets of larger than size 2, you couldn't do this exclusively with the measurement because these measurements are effectively just measuring second order properties of the vector, because what you're getting is based on the overlap, the dot products between the vector, the sketch vector and the measurement vector. So if you want to query larger sets, basically the best thing you can do is do the classical thing of sampling multiple times and hoping to hit everything in, the larger set, but taking advantage of the fact that you're able to sample pairs for the cost of sampling one thing. And indeed, this is, there's a problem called the Boolean hidden hypermatching problem, which corresponds to sampling pairs of size k, and just so with the sampling size 2 problems, it's a complexity of root n classically and log n quantumly. In general, up to some stuff about floors and ceilings that are still open, it's n to the 1 minus 1 over k complexity to sample size k pairs classically, and n to the 1 minus 2 over k to sample size pairs in the quantum setting.
Thanks, that's very informative.
Okay. Is there anything else? Okay. So that was how you construct the sets, the sketch. Sorry. For the kind of the applications, I'm going to mostly think about this as a black box. A black box sketch. and we won't have to use the underlying quantum internals too much, although I will come back later to like how you can make this sketch into something that's more useful for the stream. But first, I want to tell you about how you can use this to get advantage for a couple of streaming graph algorithms problems. So, just to make sure we're on the same page here, these are like graph problems where you have some very big graph and you're receiving it one edge at a time. And then the objective is to like answer some question about the graph while using as little space as possible. And so when you think about about quantum streaming algorithms, the natural question to ask is, are there any problems which use provably less quantum space than you'd need classical space if you wanted to solve them in the classical setting? And the very first work that considered this model actually showed that the answer is yes. You can construct quantum streaming problems that require exponentially less space than you would need classically. But this was for what you might think of as like a quote-unquote unnatural problem, by which I mean it's just a problem constructed to show a complexity separation. So the natural follow-on question is like, are there problems that people care about like classically where you get this kind of quantum space advantage? And so later there was this work by Ashley Montanaro showing you can get quantum advantage for a very natural problem, which is like this LP estimation problem when you see a stream of updates to a vector. But these advantages only arise when you have very many passes over the stream. And in particular, it's like if you have k passes, you get a square root k quantum advantage. And so what we're going to be able to do with this sketch is that we're going to be able to get quantum advantage for single pass streaming problems of kind of independent classical interest. And the first of them that I'm going to tell you about is the problem of counting triangles in the stream. So, triangles here just being another name for three cliques. And so this problem is very well studied in classical streaming. It has actually some applications in social sciences and spam detection and so on. But I think even more than that, it's been studied a lot in both the theoretical setting and some kind of more like experimental streaming algorithm settings, because it's a very natural benchmark problem. It's the simplest kind of subgraph counting problem you can think of that is non-trivial in that it requires information. You can't just write down the triangle count in a graph as a sum of like statistics of like local neighborhoods of graphs. And so this problem, and I should say this problem, to do anything non-trivial in it, you need some parameterization of it. For instance, if you just didn't have any lower bound on the number of triangles in a graph, then you wouldn't be able to do anything. And there's a lot you can say about how to parameterize it, but for our purposes, we're just going to keep it simple, and we're going to imagine a mega of m edge disjoint triangles in a theta m sized graph. And so in this setting, the hardest situation you can have is that all of your triangles share a single vertex. And specifically, what makes these kind of graphs hard is when you receive them as a very large star followed by a collection of edges that may or may not complete the neighbors of this star into triangles. Now, how hard is this? Well, you can think about what you would do in kind of like a sampling scenario. Like imagine you kept like k of the edges from this star that you see, and then you decided to check how many of them are completed into triangles by these matching edges that arise later? Well, if you kept k edges from your star, you would have a k over m all squared chance of getting any given triangle. And so since we're assuming that there are like theta m triangles, that means that you'd need k to be equal to about root m. This is, again, the same kind of birthday paradox situation we talked about before. And again, the hardness of you can prove that this is classically hard up to a log factor, or this is classically optimal up to a log factor by reducing to Boolean hidden matching. And as that connection would suggest, you can solve this in log m space with our sketch. All you have to do is sorry. You can solve it in the two-player setting, I should say. So like for simplicity, we start by like assuming that like one person has the star, they sketch it, they send it to the second person, who then uses the matching edges to try and detect triangles. And so the way you would do this is you would have the first player sketch each of the neighbors of the star, make that their set, send the log space quantum sketch to the second player, and then the second player would just query it with the set of pairs that just corresponds directly to those matching edges. And since one of the things that the sketch is letting you do is ask how many of these pairs are contained in S, the sketch tells you how many triangles there are in the graph. And so what that tells you is that there is an exponential quantum advantage for the two-player version of this like specific star and matching instance of triangle counting. Obviously, what we wanted was a streaming algorithm for triangle counting in general graphs. And so we're going to need to get rid of both that like two-player caveat and that specific instance caveat. And I want to talk about the second part of that first. So when you think about like going to general graphs, you can think separately about what you have to do to generalize like the first player's graph and the second player's graph. Generalizing the first player's graph actually turns out to be very easy. All you have to do is, so before we were making our set S be, all of these neighbors of this star vertex. Now we're going to make our set S just contain every edge in the original graph. And so then when we go to query whether the edges in the second graph form triangles with the first graph, we'll make our pairs be UVUW for every edge in the second matching and every vertex, in the whole vertex set. And this is still going to be a disjoint set of pairs because of the fact that we promised that that these edges VW are all vertex disjoint. They will form a matching. Unfortunately, it's not quite as simple to deal with the case where the edges in the second part of the graph, the second half of the stream, so to speak, don't form a matching. Because remember that we needed the fact that our set of pairs was disjoint. And so if, for instance, the second graph is say, a star on one vertex, then we don't have a valid set of pairs. We could get around this by copying the sketch, a number of times equal to the maximum degree of the second graph, and then, querying with, and then splitting the queries into one for each edge in the highest degree vertices of this graph. But that's in general infeasible because that number, that highest degree, could be as large as n. And remember that our classical upper bound was only root n. But fortunately, it turns out that the worst case instances, the ones that look like this, are actually also ones that are very easy for classical algorithms. And so I'm not going to go into much more detail about that, but basically what you can do is you can take this quantum estimator and use it to solve these instances that are hard for classical algorithms, use a classical estimator that solves these instances that are hard for quantum algorithms, and interpolate between the two. And this is unfortunately kind of lossy. So rather than like an exponential advantage, you end up with like an n to the 2/5 versus square root quantum space advantage. So it's a kind of a provable advantage, but it is a fairly small polynomial. So far, of course, this is only still for the two-player setting, and we would like something that works in the stream. For that, we're going to need to expand the capabilities of our sketch a little bit. And what we're going to do is we're going to add two extra things to it. So first, we're going to add this swap operator. So this is going to be if we name a pair xy, and if that pair is either entirely contained in the set or not in the set at all, the operation does nothing. But if exactly one of x and y is in the set, then it removes the one that's there and adds the one that's not there. And our second one is going to be a partial query operation. So previously, we had this idea of querying S with a large set of pairs and both estimating the overlap, but also sampling those pairs contained within S equally. What our partial query is going to do is, given a single pair, it's going to let us sample it with the same probability that we would have if we presented it as a large collection of pairs. But if so, that's about proportional to 1/s. But we don't want to destroy our set if our query fails. Instead, when our query fails, all that's going to happen is that we're going to remove the elements, both of the elements from the pair S, if they're present. And as in the full query setting, we're going to have the same caveat that maybe you can return P if it has only size 1 overlap with S, and it will have a ±1 sign if you do. And I should say, if you do return P, it will actually destroy the set S. So then what this is going to mean is that executing a full query, like on a big collection of pairs, is going to be equivalent to doing one of these, these partial queries one at a time. And it won't actually matter. And as long as the partial queries are disjoint, it won't actually matter what order you do them in. So I'm going to pause here, since this is this is fairly important for understanding the rest of the talk, and just check if there are any questions about what's going on here. OK. So we have these two extra operations. And these are going to let us construct and use this sketch in a streaming fashion. So for constructing the sketch, now what we can do is we'll start by before we even process any part of the stream, we're going to initialize the sketch on a number of dummy variables, which is given by the number, an upper bound that we have on the number of edges that we'll see in the stream. And then, we can maintain a counter that tells us, after seeing when you see a new edge, swap out this dummy variable for the new edge that you saw. By using partial queries, we can then query this sketch for triangles one edge at a time. So for every time you see an edge, you're going to query the sketch and ask it, does this edge complete any triangles with the input that we've seen so far? This is important for making this work in the stream, because you couldn't store all of the edges that you want to query the sketch with without blowing up your space complexity. And that gives you then this provable quantum space advantage for this triangle counting problem. You need O tilde m to the 2/5 qubits, and classically you would need root m classical bits. You can also describe this algorithm for more general settings of the parameters of the triangle problem, but the expression becomes both horrendous and not very illuminating. So I'm going to omit it here. So that's what I had to say about triangle counting. Are there any questions about that?
I believe when you were setting up the problem, you assumed that all the triangles are edge disjoint in
Yeah.
the graph. Is that inherent or?
Yes.
Okay.
So when you have a lot of triangles that overlap on an edge, that creates. So the situation where, for instance, where every triangle shares the same edge would rule out any non-trivial space advantage, at least until the number of triangles becomes superlinear in the size of the graph. And that's by a reduction to the indexing problem in communication complexity, which is equally hard for classical and quantum communication.
Okay, cool.
Thank you.
Do you need to know the length of the string beforehand?
So Santosini was asking if we need to know the length of the stream beforehand, and the answer is yes. I mean, you don't need to know it exactly. You need to know it up to a constant factor, and if you have an overestimate for it, then that would. But yeah, if you have an overestimate for it, that's going to blow up your space complexity by a proportional amount, because your sampling probability, because what you'd have to do is you have to set your sketch to be proportional to the length of the stream, and then your sampling probabilities are decreasing in the size of the sketch, which means in turn that your probability of sampling a triangle goes down by the same factor. Okay, if there are no other questions, I want to move on to saying how you would actually implement these two extra streaming properties that we said. And remember that the two things that we want to implement are swap and partial measurement. And so for this swapping operation, we will actually need to introduce an additional quantum primitive, which is this idea of unitary evolution. So if you have one superposition and you want to change it into a different superposition, you can do this by applying linear operators to the corresponding vector. But because valid states have to have length 1, these need to be length-preserving linear transformations. But it turns out, one very easy length-preserving linear transformation is just you swap a pair of basis elements. And so if you do this, so if you want to implement this swap xy operation, all you do is you apply the transformation that swaps the basis elements corresponding to x and y to the vector. So as if you remember, the sketch vector was this vector that's supported exclusively on the elements of S. This means that if x and y are both in S, you'll do nothing. If neither x nor y is in S, you'll do nothing. And if exactly one of them is in S, you will remove that one from S and add the other one to S, which is exactly what we promised for our swap operation. Okay. So then for the partial query operation, we're actually not going to need to introduce anything new. We're just going to use this same projective measurement primitive that we had before. But now we're going to care about what actually happens with this collapsing effect. So when we go to do a measurement, a partial query with a single pair xy, we're just going to measure with 3 projectors, one onto x plus y, one onto x minus y, and one onto the rest of the universe, or the rest of the vector space corresponding to the universe, I should say. So this means that your probability of returning either x plus y or x minus y is going to be exactly the same as it was when you were measuring with a big collection of projectors. But if you don't return either x plus y or x minus y, what you're going to do is you're going to project this state onto the space onto the space less the projectors onto x plus y and x minus y. In other words, the space with the span of x and y removed. And that exactly corresponds to just deleting x and y from the same S. So again, your partial queries are doing exactly, your partial query operation is doing exactly what we wanted. And that's the last quantum thing that I'm going, or the last kind of quantum primitive that I'm going to mention in this talk. So I guess, yeah, I'll stop and ask if there are any questions about that before I move on to our like last streaming application. Okay, so when we talked about triangle counting, we got like this provable space advantage, but it had a couple of caveats, right? A, it was only polynomial and not even that large a polynomial, and B, it was for like a pretty specific part of the parameter range. So here I'm going to talk about another problem where you can get exponential advantage, and that doesn't depend, that doesn't depend on parameterizing the input. And this actually is going to be for the same maximum directed cut problem that you heard about earlier this week. But just to refresh your memory, this problem is we have a directed graph, which we receive one directed edge at a time, and we want to know what is the maximum directed cut size. So a directed cut being, you assign every vertex in the graph either 0 or 1, and then an edge is cut by the directed cut if it goes from 0 to 1. So in this case, the directed cut value is 5. Feel free to check that if you want. I should emphasize here that our objective is just to output an approximation to the size of the directed cut. You don't have to return the actual description of the cut. And in particular, we care about getting an alpha approximation, defined as returning some value that's between the real value and alpha times the real value. So just to recap, what is already known about this. So, there's these results showing that if you want to get better than a 4/9 approximation, you need at least root n space classically. And then this actually older work by Frederick and Joseph shows that you can actually get better than a 4/9 approximation if you have this snapshot of the graph, or what we can also call a first degree bias histogram. So this is like a count of how many edges go from vertices of kind of one range of biases to another. And I'll be a bit more specific about that in the next slide. And of course, as you saw earlier this week, this root n lower bound is actually also tight. You can get a root n space streaming algorithm that achieves it. And what I want to tell you about is a result saying that you can actually estimate this histogram and therefore get a better than 4/9 approximation to the max cut value in polylog n space by using this same sketching primitive. And so to describe how you do that, first I want to get a bit more specific about this kind of idea of a histogram of biases. So just hold the definition of the bias of a vertex is it's the difference between its in degree and its out degree and its in degree normalized by the degree itself. And so then the problem that we're trying to solve with this streaming algorithm is that we're given a partitioning of the biases into, so the biases range from -1 to +1. We're given a partitioning of them into these contiguous chunks. And we want to know, for each pair of these chunks, how many edges there are that start in one bias class and go to another bias class. And so to explain how you can do this with a quantum algorithm, I want to return to this 2-player setting that we started with, the Alice and Bob setting, and think about just having Alice and Bob both having graphs, and Alice trying to send Bob a short description of her graph that will let him estimate how many, estimate the bias histogram of their joint inputs. So estimating how Alice's edges contribute to this histogram is actually very easy, because what Alice can do is she could just randomly sample her edges, and then to each of those samples, she would attach the biases and the degrees of the two endpoints, send them over to Bob, and he could then look at his own input and say, okay, well, what are the biases? Since I know the bias in the degree analysis graph, I'll find out what the bias is in the graph as a whole using my graph. and then slot them into the right place in this histogram. So the challenge then is figuring out how to sample these like head-tail degree pairs, degree and out degree pairs, so bias and degree pairs from Alice's graph corresponding to individual edges in Bob's graph, so that we can figure out how Bob's edges correspond to this histogram. And what we can do is, and here we're going to start by thinking about, again, this easy case where Bob just has a matching, is we could use our sketch to sample like labeled pairs of Alice's vertices corresponding to Bob's edges. So Alice would like sketch her vertices along with their like biases and degrees, and she would then send those along to Bob, and Bob would like sample from it using this like set of pairs. I should say that like actually implementing this requires like a bit of extra work, because you have to like coarsen Alice's possible biases, because our sketch doesn't actually let you say, oh, I want to sample a vertex V and then tell me its label. You actually have to name its label when you sample it. But as long as you only need like a limited resolution of Alice's biases, this is not that big a problem. The bigger problem is that, well, in general, Bob doesn't have a matching. So what can we do if Bob does not have a matching? Well, this time we actually have what we can do, or this time, we can actually do something a bit nicer than what we could do in the triangle counting case. And we'll start by like imagining that Alice knew how many edges Bob had incident to each of her vertices. If she did, what she could do is she could copy each of her vertices with multiplicity equal to Bob's, that vertex's degree in Bob's graph, and sketch, all of those copies. Bob could then, when he went to measure, he could like copy each of his matching, each of his pairs in the same multiplicity, so he'd still be, obeying the disjointness rule. And this wouldn't actually cause any problems for our complexity. Remember that like sketching more things is in general not optimal, because it decreases your probability of sampling, since that's like 1 over the size of the set. But because the sum over Alice's vertices of Bob's degrees is at most the number of edges in the graph, she'd still be sampling with probability like 1 over total number of edges in the graph. And so she'd still be able to get like an accurate estimate of this histogram. The problem, of course, with this approach is that Alice doesn't actually know what Bob's degrees her vertices are going to have in Bob's input. But what she can do is use her own degrees as a proxy for Bob's degrees. Now, there aren't actually any guarantees on how her degrees are going to correspond to Bob's degrees. So how is this useful? Well, it's useful because in the case where the degree of a vertex in her input is much smaller than the degree of a vertex in Bob's input, then her input doesn't actually matter at all, because the bias of a vertex is going to be, the bias of any given vertex in the unified graph will be determined by Bob's input in the case where its like degree in Bob's input is much higher. So what that means then is you can combine like a classical sampling approach where that like handles all of the cases that this quantum protocol is useful for, with this quantum sampling protocol to solve this like 2-player bias histogram estimation problem in only polylog of n space. And the reason this is polylog of n space rather than log n space is because we kind of have to do something different for each degree Alice's vertices can have. So we kind of split it into like this exponentially increasing set of degree classes. But I'm gonna brush over the details of that. And instead, what I want to move on to for the final part of describing this algorithm is how you can actually do all of this in a streaming setting. So Ideally, based on this description, what we'd like to do in the streaming setting is maintain a sketch of the vertices in the graph that come attached, where like each vertex has, this Coarsen description of its bias, and where each vertex bias pair is maintained in multiplicity corresponding to the degree of that vertex. Then, as we see edges coming in, we would like to, measure for each edge UV. We'd like to do a partial query of U bias of U, V bias of V, or for each possible, Coarsen value of the bias of U and the bias of V, and then once we get one of these samples, we can then look at which edges are incident to that vertex and the rest of the stream and get a final estimate of its bias, which we'll plug into our estimate of the bias histogram. And then, we can just do some classical sampling stuff to, deal with all of the cases where these biases are dominated by edges that arrive after UV. So this corresponds to the case in the two-player setting where Bob's degree for a vertex was much higher, and therefore Bob's input determined the degree of that vertex. The problem with this approach is that we can't actually do this first part. If we wanted to maintain this set of vertices, this set where each vertex appeared in multiplicity corresponding to its degree, we would need to actually know this degree when we see an edge UV. And by know this degree, I mean even you would only need to know the degree in edges that arrive before UV, but even that is something that you can't actually legally maintain because you're not allowed to use the omega of n space it would require. So instead, I want to kind of describe at a very high level how you can get around this problem. And for the remainder of this slide, just kind of assume that instead of trying to maintain biases, I'm just trying to maintain the degrees of vertices. So the idea is that you want to maintain each vertex in multiplicity equal to its degree. So what you're going to do is you're going to copy each vertex. You're going to add a copy of each vertex to the set S every time you see an edge incident to it, and you're going to use the number of times that you've done this to encode its degree. So the way that you'll do this is that when you add a vertex to S, you'll always add it with this label that says 0. And you'll also increment every copy already in S, the label of every copy already in S by 1, which you can do with these swap operations. And so that means that now for each vertex, S will contain vi for every I from 0 to the degree of the vertex in the input you've seen so far. And so then you can query whether this vertex exists in the set with degree at least some threshold by doing queries that specify this threshold degree label in them. Now, doing the actual algorithm becomes actually quite a bit more complicated because what you care about is the biases, not just the degrees. So you need to do this separate thing to encode the out degrees of the vertex, and it's unfortunately not possible to do this by just repeating that. But I'm going to kind of skim over the details about how you do that, since they're not that enlightening, and just give you the final result, which is that there is a polylog n space quantum streaming algorithm that successfully approximates this bias histogram, and that therefore gives you a better than 4/9 approximation to the maximum die-cut value of the graph. And I want to note that this is in contrast to what you get with the undirected version of Max-Cut, where you can actually prove that there is no quantum advantage possible for any approximation ratio that you would care about. So that brings me to the end of what I wanted to talk about. So just to wrap up here, we have a simple log space quantum sketch that allows you to solve the problem of sampling pairs from a set with the same complexity that classically you'd need to sample singletons. It gets you some quantum space advantages for this for the problem of counting triangles in the stream. It gets you exponential advantages for the streaming version of directed cut. And now just a couple of open questions. One, what is the correct complexity for triangle counting? Because our lower bounds that we know still leave open the possibility that you could get an exponential quantum advantage for this problem. And second of all, is there a way of like characterizing which constraint satisfaction problems admit quantum space advantage? Because we've seen that directed cut does and regular max cut doesn't. Maybe there's like some property that you can describe that tells you when these advantages are possible. And that's all I wanted to say. So thank you for listening.
Questions for John?
I have a question regarding the approximation ratio you just briefly mentioned. So is that gonna, for different approximation ratios, is that gonna change the quantum advantage, say from exponential quantum advantage to just polynomial advantage?
So below 4/9, there's a classical algorithm that achieves that in polylog n space. Above 1/2, the same results that tell you that you can't get quantum advantage for max cut would also tell you that you can't get quantum advantage for this problem. And between this 0.435 and 1/2, the question is still open, just as it is in the classical setting.
Okay, gotcha. Thanks.
Can you use these type of techniques to get like dynamic, like insertion deletion algorithms?
So the sketch is inherently a bit hostile to deletions. Okay, so when you think of inserting things into the sketch, there you could get insertion and deletion with the caveat that you would pay, that your like price would be the total number of updates rather than the total number of edges. Because basically what you could do is you could say, okay, I'm going to do a swap operation that takes this thing I want to delete and turns it into junk. If you know that you're only going to delete stuff that is definitely there, then you could transform it back into a dummy edge and maybe not pay that overhead. But the bigger problem is that the measurement operators are irreversible. So I'm not aware of any like general approach that you could use to make either of these algorithms work in a dynamic setting, because they depend on doing the measurements one at a time.
Thanks. Any other questions?
I think it's related to the last question, and also it may be a silly question. Is there a quantum advantage if I don't allow my sketch to be destructive? Like, or is there an impossibility theorem saying you can't?
Are you asking? I guess I'm not sure how to think about. I guess I'm not sure how to understand what the answer to that should correspond to. Like, so this sketch very much depends on doing measurements which are inherently a destructive thing. You could, in principle, imagine a streaming problem where there was a quantum advantage that came from an algorithm that did all of its measurements at in post-processing, and that therefore allowed insertions and deletions, and therefore was not destructive while processing the stream. But I'm not aware of any problem that evinces such an advantage. Certainly, these ones definitely depend on the destructive nature of the measurements.
I think a natural setting would be if I have multiple queries doing the stream, then is it just impossible to handle it with quantum extension?
Well, if you have a query that like if you have a query that's not destructive, then it's in some sense an inherently classical query. So I mean, I maybe I'm not understanding the setting you're thinking of correctly, but I don't think there's. But so when I say destructive, I mean like, as in it permanently modifies the sketch. Like it's not like as we saw in like the partial query sense, it's not necessarily like making the sketch totally useless, but yeah, like the fact that quantum measurements change the state you measure is you know, inherent to how they work.
Hi. So if I understand correctly, like for the Max-Cut lower bounds, it's like if we want to beat half approximation for both classical and quantum, it requires omega n space, right?
That's right. Yeah.
I guess if we're in the setting where like we allow for omega n space and like maybe want to do like some sort of like epsilon approximation, I guess, is it possible there's like a quantum like space advantage if we like consider dependence on epsilon? Like, is that something we even care about?
So in terms of the dependence on epsilon, I guess I don't know of any lower bounds that would rule that out. Because yeah, like if you have omega of n space, I think like classically you can get like n over epsilon squared is I think enough to get you there just by doing like uniformly subsampling the edges. I would guess that that's probably optimal for the classical setting, but for the quantum setting as well. But I haven't thought about it in detail.
Okay, let's thank John once again.